Our goal for this presentation is to explain the background of Android smartphones and their operating system. Due to the rapid growth of smartphones and their application markets, it presents many security challenges. We want you to understand how Android security works and what you can do as an individual to make your smartphone more secure.
We will now show you a short video that overviews mobile security and some information we want you to know.
We will now go more in depth with Android devices.
Android layout. Android is an OS designed for smartphones. In the picture to the right, it displays the sandboxed application execution environment. Sandboxing is a security mechanism for separating running programs, often used to execute untested or untrusted programs of code. A customized embedded Linux system interacts with the phone hardware and an off-processor cellular radio. The binder middleware and application API runs on top of Linux. To simplify, an application's only interface to the phone is through these APIs. The phone comes pre-installed with a selection of system applications such as phone dialer, address book, etc. Each application is executed with a Dalvik virtual machine, DVM for short. Application interaction. Applications interact with each other and the phone through different forms of IPC. IPC stands for Inter-Process Communication. It's a set of programming interfaces that allow a program to coordinate activities among different program processes that can run concurrently in an operating system. This allows a program to handle many user requests at the same time. Then, the binder acts as a mediation point for all IPC. The permissions requested by the application and the permissions required to access the application's interfaces/data are defined in its manifest file. Access to system resources such as GPS receivers, text messages, the internet, etc., and IPC is governed by permissions assigned at install time. To simplify, an application is allowed to access a resource or interface if the required permission allows it. Permission is usually delegated to the phone owner. The Dalvik virtual machine. Android applications are written in Java but run in the DVM. The DVM and Java bytecode runtime environments differ. The JVM loads the bytecode for a Java class from the associated class file as it is referred at runtime. However, the Dalvik application consists of only a single DEX file, which contains all the application classes. After the Java compiler creates JVM bytecode, the Dalvik DX compiler consumes the class file, recompiles them to the Dalvik bytecode, and writes the resulting application in a single DEX file. The image to the right provides a conceptual view of the compilation process for the DVM applications. The DVM is a register base, whereas existing JVMs are stack-based. Java bytecode can assign local variables to a local variable table before pushing them onto an operand stack for manipulation by opcodes. Opcodes are the portion of a machine language instruction that specifies what operation is to be performed by the CPU. The Dalvik opcodes directly manipulate registers, rather than accessing elements on a program stack. The Dalvik bytecode instruction set is substantially different than that of Java. Dalvik has 218 opcodes, while Java has only 200. However, the nature of the opcodes are very different. For example, Java has tens of opcodes dedicated to moving elements between the stack and local variable table. Dalvik instructions tends to be longer than these Java instructions. As a result, Dalvik applications require fewer instructions. In these applications, on average, they have 30% fewer instructions than Java, but have a 35% chance larger code size.
We will now look at how we can evaluate Android security. The following are 4 approaches to evaluate recovered source code for evaluating Android security: control flow analysis, data flow analysis, structural analysis, and semantic analysis. In using these 4 different types of analysis, we can explore issues uncovered in previous studies and malware advisories, search for general coding security failures, and explore misuse or security failures in the use of Android framework. Control flow analysis. This analysis imposes constraints on the sequences of actions executed by an input program P, classifying some of them as errors. Basically, control flow automaton A, whose input words are sequences of actions P. The rule monitors executions of P. An erroneous action sequence is one that drives A into a predefined error state. To statically detect violations specified by A, the program analysis traces each control flow path in the tool's model of P, synchronously executing A on the actions executed along this path. We did something similar to this in Computing Systems 1 when we were evaluating buffer overflows and buffer attacks. In this figure here, the error state is reached if the intent contains data and is sent unprotected without specifying the target component. This would end up resulting in a potential unintended information leak. Data flow analysis. This permits the declarative specification of problematic data flows in the input program. The specification declaratively labels program statements, matching certain syntactic patterns such as data flow sources and sinks. Flows between sources and sinks cause violations. For clarification reasons, a data source is the location where data is being used comes from. This data source for a computer program could be a file, a data sheet, a spreadsheet, an XML file, or even hard-coded data within the program. A data sink is a term used to describe a computer or any other medium capable of receiving said data. Structural analysis is what we're used to doing every day in computer science. This allows for declarative pattern matching on the abstract syntax of the input source code. This type of analysis is not concerned with program executions or data flow, allowing for easy analysis. Semantic analysis. This allows for the specification of a limited set of constraints on the values used by the input program. An example of this can be such as an Android app that does not send SMS messages to hard-coded targets. Semantic specifications allow us to directly specify that the first parameter in these calls is not a constant. The analyzer then detects violations using constant propagation techniques. The following are examples of mobile misuse. Abuse of telephony services, such as telemarketers or receiving texts from numbers that you don't have saved, are examples of smartphone malware that has sent SMS messages to premium rate numbers. Botnet characteristics. PC botnet clients historically use non-HTTP ports and protocols for command and control. We can examine Socket for suspicious behavior in these circumstances. Lastly, we have general Java application vulnerabilities. This includes misuse of passwords, misuse of cryptography, and traditional injection vulnerabilities. This is the most common example of mobile misuse, as we are told almost every day that we should not have short passwords but rather lengthy ones that don't consist of normal letters. That way, our information cannot be stolen so easily. Socket API misuse. For clarification, a network socket is an internal endpoint for sending or receiving data within a node on a computer network. Java sockets represent an open interface to external services, so they are easy targets for malicious behavior, such as honeypots. An example can be something that many of us in the class have already done, such as jailbreaking a smartphone. Downloads from third-party applications that are not on the Google Play Store or the App Store can also contain botnets or other malicious activity that can harm your device. When researching this topic for our presentation, we found two findings that were particularly interesting in cybersecurity. The first finding concluded that a small number of applications include code that uses the socket class directly. Some of these applications were flagged for inclusion of well-known network libraries, such as org/apache/thrift.org/apache/commons and org/eclipse/jetty. The second finding, however, found that there was no evidence of malicious behavior by applications using the socket directly. The socket can also be used for things such as file transfer protocols, chat protocols, audio and video streaming, and network connection tethering.
Now we will talk about Android-specific vulnerabilities. The first one is leaking information via IPC. The image to the right shows how any application can receive intent broadcasts that do not specify the target component or protect the broadcast with permission. This is unsafe if the intent contains sensitive information. About 8.4% of applications have such intent and install shortcuts to the home screen. The next one is unprotected broadcast servers. Applications use broadcast receiver components to receive intent messages. Broadcast receivers define intent filters to subscribe to specific event types that are public. If the receiver is not protected by permission, a malicious application can forge messages. Intent injection attacks. Intent messages are also used to start activity and service components. An intent injection attack occurs if the intent address is derived from an untrusted input. And lastly, delegating control. Applications can delegate actions to the other applications using a pending intent. An application first creates an intent message as if it was performing the action. It then creates a reference to the intent based on the target component type. The pending intent recipient cannot change values, but it can fill in missing fields. Therefore, if the intent address is unspecified, the remote application can redirect an action that is performed with the original application's permission. Apple vs. Android security. Apple's App Store has proven to be safer than Android's because their applications are fully vetted before being made available to customers, which has prevented widespread malware infections. The Google Play Store, which is available for Android users, contains the ability to install apps from third-party sources. Some can be as well-known, such as Amazon. However, others are not and originate from malware hotspots, such as Russia and China. Criminal developers can deconstruct and decompile popular apps, such as Angry Birds, and publish malicious versions and make them available for free. The biggest mobile security news of the past year concerned the iPhone and Apple's approach to security. When Apple refused to unlock an iPhone 5C for the FBI, the conversation around its encryption practices moved center stage. In response to the FBI request to unlock an iPhone, Apple reportedly strengthened its encryption around iCloud and hardware to make it even harder to hack. Also, Android is working to become more secure. In realizing Android's business potential, Google has made a plethora of changes to its mobile OS recently to beef up its security. Google recently announced automatic security updates for Android, which makes it quicker and easier to patch applications. Also, Google has said that they are working hard to rid its App Store of harmful apps. What you can do to protect your mobile devices from malware. Number 1. Inform users about mobile risks. Users often don't realize a mobile device is a computer and should be protected like one. Always consider the source of an app or a game before you download it. Number 2. Consider the security of over-the-air networks used to access company data. Wi-Fi networks are insecure generally. For example, a user is accessing corporate data using free Wi-Fi at an airport. The data may become exposed to malicious users sniffing the wireless traffic on the same access point. Therefore, you should be cautious when accessing sensitive data over a public Wi-Fi network. Third, prevent jailbreaking. Jailbreaking is the process of removing the security limitations imposed by the operating system vendor. This means breaking the security model and allowing all apps, including malicious ones, to access the data owned by other applications. Number 4, encrypting your devices. The risk of losing a device is still higher than the risk of malware infection. Protecting your devices by fully encrypting the device makes it incredibly difficult for someone to break in and steal the data if you ever lose your phone. And lastly, encourage users to install anti-malware on their devices. Although malware exists for devices that run iOS, this operating system interface doesn't support anti-malware software. However, the risk of infection is highest for Android, where security software is already available. Make sure all your Android devices are protected by anti-malware software. To conclude our presentation, we will now show a video about one of the many anti-malware softwares that you can download for your Android device. This one is called Zimperium.